Hi, and welcome to this talk on signals in the frequency domain. In a previous lesson, we looked at the time domain waveforms for common sinusoidal carrier modulations. However, if you're interested in the spectrum of these signals, what you want to know is what's happening in the frequency domain, and that's what we'll address in this lesson. The key parameter of spectrum utilization is bandwidth, and as we'll see, bandwidth can be a slippery concept, so we'll have to address that first. Then we can get down to business. We'll go over the spectrum and bandwidth of a few common signals, including the unmodulated carrier, AM, ook, and BPSK. When it comes to digital modulations using amplitude or phase modulation, we'll see that these all have very similar spectral properties. And for these modulations, we'll also need to say a little bit about the concept of pulse shaping. We'll wrap up the discussion of digital modulations by defining the concept of spectral efficiency, which is how many bits per second we can send per unit of bandwidth. Finally, we'll talk about frequency modulation. And with that, you should have a decent idea of how to assess the bandwidth of most common modulations. Let's get started. First, what do we mean precisely when we say that a signal has bandwidth? Formally, one might say that the bandwidth of a signal is the width of the contiguous spectrum that a signal occupies. However, that is not as clear-cut a definition as you might first think. And in fact, there's no obvious definition of bandwidth. Let me begin with an example. Here is a very typical spectrum that you might encounter for a signal in the wild. By spectrum, we of course mean power spectral density, that is, watts per hertz as a function of frequency. What we see here is a lot of power in a main lobe near the center frequency, and then side lobes extending in both directions away from the center frequency and getting progressively weaker. Again, a pretty typical thing to see. So, what is the bandwidth of this signal? Well, a direct application of our definition would say that the bandwidth is potentially infinite, since we can't see the side lobes go to zero and stay zero with changing frequency. So, this is obviously not a satisfactory definition. A fairly common way to define bandwidth in practice is in terms of half-power bandwidth. In this scheme, you say the bandwidth is the distance between the points in the average spectrum at which the power density is down by a factor of 1/2 relative to the maximum. This is sometimes alternatively called the 3 dB bandwidth, or full width at half maximum. These all mean more or less the same thing for a sinusoidal carrier modulation having spectrum that is symmetric around the carrier frequency. While this definition is common, it is also a bit problematic, in particular for what we want to do here, in that it ignores a lot of the power, namely the power beyond the half-power points. Another way to go is to define bandwidth as a contiguous range of frequencies that contain a certain fraction of the power. For example, the 99% bandwidth is the frequency span containing 99% of the power of a signal. That's typically significantly greater than the half-power bandwidth. The principal advantage of this definition is that you know for sure how much power you're not considering, and it will be the same amount of power regardless of the shape of the spectrum. The principal disadvantage of this definition is that it is relatively difficult to calculate. Essentially, you have to integrate over the shape of the spectrum to figure it out. Yet another common way to define bandwidth is as the width of the main lobe. This is called the first null bandwidth, or FNBW. This definition is obviously very convenient for this particular signal, and in fact we can find a use for this definition later in this lesson. However, we see once again that there's a catch, and that is that there are many signals that have spectrum which do not have discernible nulls. So, what are we going to do? Well, commonly, we avoid making a firm definition and simply agree that bandwidth means whatever value accounts for effectively all of the signal. Now, obviously, effectively all is subjective. This may seem vague, and it is, but this works well enough for a lot of practical work, including what we need to get done in this lesson. But let's be clear about one thing. If your concern is practical spectrum management, you need to do more. Simply put, spectrum management is all about knowing how much power lies outside a specified frequency range. So Just know that when it comes time to do practical spectrum management, you're going to have to tighten the screws on our definition of bandwidth. Okay, now let's get to it. The first and simplest signal we can consider is the unmodulated carrier. Now, just to remind you, an unmodulated carrier is simply a sinusoid that has all three parameters, that is, frequency, magnitude, and phase, all equal to a constant. In other words, this is what you get when you stop sending information, but continue to transmit. And here's what we see. Once again, this is a plot of power spectral density versus frequency. In this case, all the power is packed into a single frequency, so we just see a vertical line. Since the power is all at one frequency, you can compute the power as simply being the time average energy of the signal. That is, you just square the signal and average over time. The key point here is that when you see a vertical line like this in the spectrum, there's a pretty good chance you're looking at an unmodulated carrier. Another possibility is that such a line in the spectrum is a spurious signal generated by either some device out there in the environment, or maybe it's something being generated internally to your receiver. Both possibilities are pretty common. Okay, now amplitude modulation. A common use for AM is to send voice audio, so let's consider that first. This plot shows you what you can expect for the spectrum of low fidelity voice. Typically, you need frequencies from near zero to about 3 kilohertz in order for voice to be easily understood. Let's call the associated bandwidth of this voice signal W. So we'll say W equals 3 kilohertz. Now what AM does is to modulate the carrier amplitude using this voice signal. If you do this using double sideband large carrier AM, then this is what we get. First, we see the carrier, and that's of course totally expected. But now we also see a copy of the audio spectrum appearing to the right of the carrier. And we see yet another copy of the audio spectrum, spectrally reversed, to the left of the carrier. We refer to these two copies of the audio spectrum as sidebands, and we say that DSBLC has upper and lower sidebands. These sidebands each have width W, so the overall bandwidth of the DSBLC signal is about 2W. That is, since W is about 3 kilohertz, we find that double sideband large carrier AM has bandwidth of about 6 kilohertz when we use it to send voice signals. Now, recall our previous discussion about the messiness of bandwidth definitions. All we are saying here is that effectively all of the power lies within 6 kilohertz. In fact, the audio bandwidth has some energy lying beyond 3 kilohertz, and so there is some energy lying more than 3 kilohertz away from the carrier. In a practical system, we're going to need to account for this. So you'll see that when DSBLC is used in practical systems, the channel spacing is typically 10 kilohertz. This is obviously much greater than the 6 kilohertz that appears to be needed to send the information, but you want that margin to account for the power that you can't help sending because the formal bandwidth of practical signals is always greater than the bandwidth that accounts for the useful power in the signal. This is a theme you'll see repeated over and over again in practical radio systems. We have a bandwidth that contains the useful part of a signal, but then we need to make channels that are larger because this power extends beyond these limits. The other form of double sideband AM is the version where we suppress the carrier. The obvious effect on the spectrum would be simply that the carrier disappears, as indicated here. Since we still have both sidebands, the bandwidth and the channel spacing remain the same. In single sideband AM systems, we dispose of one of the sidebands. Now you should see why this is possible and also why it makes sense to do this. Since each sideband is a complete copy of the audio spectrum, you don't lose any information by suppressing one or the other of the sidebands. In this case, we've suppressed the lower sideband, which yields what we call upper sideband modulation, or USB. If instead we suppress the upper sideband, we end up with what we call lower sideband modulation, or LSB. In either case, we've reduced the bandwidth of the signal from 2 times W to just W, so just 3 kilohertz. In turn, this allows us to reduce the channel spacing. Typically, we use 5 kilohertz in practical systems. And the benefit of SSB should be clear. With just a little bit of additional complexity, we are able to send the same amount of information in half the bandwidth. For completeness, let's do vestigial sideband AM. You may recall that VSB is used for the video portion of the analog TV signal in North America, also known as NTSC. In NTSC, the bandwidth of the video signal is about 6 MHz, with only the upper sideband retained. Since this is VSB, we also retain the carrier, which is used by the receiver as a frequency and phase reference. The resulting bandwidth is approximately 6 MHz. Okay, now let's consider two modulations that are very similar, ook and pulsed CW. As you may recall from a previous lesson, ook is a digital modulation in which the carrier is turned on or off to send each of the two possible symbols. However, it is a special case of a broader class of modulations known as pulse continuous wave, or simply pulsed CW. Another common use of pulsed CW is for L-band aviation radar. In either case, the carrier is turned on or off with a symbol period t. One thing we're going to assume here is that the time average of the waveform is 0. You'll see why that's important in a few minutes. Here's what we see in the frequency domain. We refer to this type of spectrum as sync spectrum. That's sync spelled S-I-N-C, meaning sign of an argument over the argument. We see sync spectrum when we have a carrier that changes state periodically, but is constant between those state changes. And that's exactly what's happening in ook, and it's also what's happening in pulsed CW. Sync spectrum consists of a main lobe centered on the carrier frequency, with first nulls that are separated by 2/t. For this reason, it's often convenient to specify the bandwidth of sync spectrum in terms of its first null bandwidth, which in this case is just 2/t. The main lobe is surrounded by side lobes of decreasing strength, and each side lobe has a width of 1/t. Also note that the power spectral density of the closest side lobes is 13 dB down. 13 dB is a factor of 20, so what we're seeing is the first side lobes are weaker by a factor of 20 in power. One other thing to mention before moving on. The first null bandwidth is 2/t, but generally we could say the bandwidth is inversely proportional to t. Now, the rate of information is proportional to 1/t, so what we're seeing here is that bandwidth is proportional to the rate of information. For example, if we were to double the bit rate, then we would expect the bandwidth to double. This will be a recurring theme in digital communications. In the previous slide, I noted that we assume the time average value of the waveform is 0. Now, this is only true if each symbol consists of an integer number of periods of the carrier. If this is not exactly true, and it typically is not, then you end up with a small fraction of a period left over in each symbol. In this case, the time average value of the waveform will not be exactly 0. This leads to the condition illustrated in this slide, known as carrier breakthrough. When you have carrier breakthrough, the signal is essentially the sum of an ideal version of the signal, as shown on the previous slide, plus a residual amount of carrier that is unmodulated. You end up with spectrum as shown here, which is the same as before, except now with that little piece of carrier poking up at the center frequency. Now let's consider a different digital modulation, BPSK. Recall that in BPSK you have, once again, two symbols, but in this case the two symbols have the same carrier magnitude, but opposite carrier phases. Once again, we assume the symbol period t and a time average value of the waveform of 0. What do we see in this case? Well, the answer is we see almost exactly the same thing we see for ook. The only difference is that the power spectral density goes down by a constant value of 2. This is because the carrier is on 100% of the time for BPSK, but it's on only 50% of the time for ook. Other than that constant level shift, everything looks the same. What does it mean that ook and BPSK give us sync spectrum? What it means is that the spectrum is determined entirely by the fact that we hold the carrier constant between the symbol boundaries. What the values of the magnitude or phase are during that time is irrelevant. just as long as they don't change within the symbol period. So if we have that property, then we're going to end up with sync spectrum. In fact, now we know that this result applies to all digital modulations for which either phase or amplitude is used to send information, and phase and amplitude remain fixed over the symbol period. So this is what you also see for QPSK, and also what you see for QAM with any number of symbols. All that matters for such modulations is the symbol period. So now you ask, why is it that the symbol period is what determines bandwidth? Well, just consider this. Within each symbol period, we have essentially an unmodulated carrier, that is, a simple sinusoid. That is, if we computed the spectrum using data taken entirely within a symbol period, we would find that bandwidth is 0. Therefore, the bandwidth is due entirely to the transitions between symbols. It's the abrupt change in the waveform going from the previous symbol to the next symbol that accounts for the bandwidth. Once you realize the bandwidth is due entirely to the abrupt change in the waveform at the symbol boundaries, this raises the question, is it possible to reduce the bandwidth by smoothing out those abrupt changes? Well, the answer is absolutely yes, and this is called pulse shaping. The idea is that before, without pulse shaping, the waveform is simply a set of time-limited symbol waveforms that we add together, as shown in this slide. The harsh transitions arise because each symbol waveform is defined separately from the adjacent waveforms. In pulse shaping, we let the symbol waveforms extend into the adjacent symbol periods. Then we add them up, and we have a gentle transition from one symbol to the next. Of course, we also have overlapping symbol waveforms, so there is the potential for interference between symbols. This leads to a waveform design problem that's beyond the scope of this lesson. However, that problem has a solution, and in fact it has many solutions. And in those solutions, the symbols are both overlapping and do not interfere with each other. One common class of these solutions is known as raised cosine pulse shaping. Here's a comparison of what we get without pulse shaping on the left versus what we get with a scheme like raised cosine pulse shaping, shown on the right. In raised cosine pulse shaping, we set a parameter known as the roll-off factor, little r, which controls the abruptness of the transition between symbols. At one extreme, r equals 1 corresponds to no pulse shaping, and that gives us the result on the left. At the other extreme, r equals 0 corresponds to the smoothest possible transitions. For values of r less than 1, we have the result shown on the right, which is now seen to have a first null bandwidth of 1 plus r over t, as opposed to 2 over t before. Since r is between 0 and 1, we can see that the bandwidth can be as little as 1 over t using pulse shaping. So we found a way to reduce the bandwidth by as much as a factor of 2 using this technique. Now, you might ask, why not always use r equals 0, since that would always give the minimum bandwidth? Well, the answer is that there is a trade-off, and the trade-off is that the smaller r becomes, the more extended the symbol becomes in time. This makes it harder to generate the symbols, and it also makes it harder to design receivers that can optimally receive the symbols. In practice, a typical value for the roll-off factor ranges from about 0.1 to about 0.6. Aside from first null bandwidth, note that there's a few other characteristics of the waveform that are affected. First, side lobes go way down. The first side lobe level is reduced from 13 dB to a much smaller number. This is obviously great news if you're interested in trying to pack these signals close together because you have limited spectrum. At the same time, you also see that the main lobe becomes flatter. This is the hallmark of pulse shaping. When you see a flattened main lobe, you can bet that you're looking at a phase amplitude digital modulation with pulse shaping. And even though we started talking about this in the context of BPSK, keep in mind that this applies to any phase amplitude digital modulation, up to and including all the various quadrature amplitude modulations having any number of symbols. A common consideration in radio engineering is spectral efficiency. Spectral efficiency is the data rate that can be achieved per unit bandwidth. This is something we can work out for the type of digital modulations we've been considering. It goes like this. Bandwidth is 1 plus r over t, where r is between 0 and 1, and is equal to 1 for no pulse shaping. And each symbol in a digital modulation sends log base 2 of m bits, where m is the number of symbols. So for example, m equals 2 for BPSK, so we send 1 bit per symbol. But m equals 4 for QPSK, so for QPSK we send 2 bits per symbol. In any event, the bit rate is simply log base 2 of m divided by the symbol period t, and that gives us the bit rate in bits per second. So, spectral efficiency is bits per second achieved by the modulation divided by the bandwidth that's required. And if we use the first null bandwidth as our bandwidth metric, then spectral efficiency is log base 2 of m divided by 1 plus r, and that gives us spectral efficiency in bits per second per hertz. So here an example is useful. Let's say we're using BPSK, and we want to send 10 megabits per second using raised cosine pulse shaping with roll-off factor 0.35. Now we want to know the bandwidth and the spectral efficiency. And also, we would like to know what would be different if we switched to QPSK. The solution is as follows. First, we find the symbol period t is simply 1 over the bit rate, so t is 100 nanoseconds. The first null bandwidth then is 1 plus r over t, which is 13.5 megahertz. The spectral efficiency is then 0.74 bits per second per hertz. In other words, for each hertz of spectrum that we're using, we're sending 0.74 bits per second. Now, we really can't point to those bits in the spectrum, but nevertheless, this number tells us how efficient our use of spectrum is. Finally, what happens if we change to QPSK? Well, the only thing that changes is we go from 2 symbols in the constellation to 4 symbols in the constellation, which means we're sending 2 bits at a time as opposed to just 1 bit at a time. The bandwidth and the spectrum shape are unchanged because neither the symbol period nor the roll-off factor changed. What changes is the spectral efficiency, since now we're sending 2 bits per symbol as opposed to 1 bit per symbol. Specifically, the spectrum efficiency is doubled to 1.48 bits per second per hertz. There's one important form of modulation that we have yet to address, and that's frequency modulation. Unlike AM and phase amplitude digital modulation, it's quite difficult to come up with a simple description of the spectrum of frequency modulation, especially for analog frequency modulation. However, there is a handy equation for estimating the bandwidth of analog FM signals that you should probably know about, and that's called Carson's rule. This rule can be written in a few different forms, but the one I suggest for most work is the one shown here. Bandwidth is approximately 2 times beta plus 1 times W. As before, W is the bandwidth of the audio signal. Beta is what we call the modulation index, and that's a measure of how much the frequency of the carrier changes in response to changing in the amplitude of the audio. In other words, beta is a property of the modulation. Now to see how this works, let's do some examples. For our first example, let's just consider FM broadcast. And this is one of those signals around 100 megahertz that you would typically listen to on your car radio. The whole point of FM broadcast is high fidelity, so the audio bandwidth W is increased to 15 kilohertz. The modulation index in this case is 5. So Carson's rule tells us the bandwidth is roughly 180 kilohertz. Now, if you've ever used a car radio to listen to FM, you know that the FM stations are separated by 200 kilohertz. For example, 89.1 megahertz, 89.3 megahertz, 89.5 megahertz, and so on. And now you know why that spacing is 200 kilohertz as opposed to simply 180 kilohertz. That is, we need to accommodate that small amount of power that lies outside the range of frequencies that we consider to be useful. By the way, we say that in general, if beta is greater than 1, then we have wideband FM. And this is commonly abbreviated WB-FM. So, broadcast FM signals are said to use wideband FM modulation. Here's a second example that addresses a very important class of signals. These are the land mobile radio signals that appear throughout the VHF and UHF bands, and these signals are very common. For these systems, we're back to 3 kHz audio, and the modulation index is about 1. In this case, Carson's rule tells us to expect about 12 kHz of bandwidth. Typically, the signals are spaced by about 25 kHz. Now, that's a lot of margin in this case, which should tell you something about the uncertainty in how much power is ending up outside that nominal 12 kHz that we consider to be occupied. By the way, when the modulation index is much less than 2 pi, as it is here, we consider this modulation to be narrowband FM, and that's abbreviated NBFM. Wideband FM and narrowband FM entail some significant differences in implementation. That brings us to the end of this lesson. Let's briefly review. First, we addressed the slippery concept of bandwidth. Remember, caution is required when interpreting numbers assigned to bandwidth. We talked about the unmodulated carrier, which produces a single line in the spectrum and has essentially 0 bandwidth. We talked about AM, and we saw that the bandwidth was typically between W and 2W, depending on whether we kept one or both sidebands. Then we talked about phase amplitude digital modulations, and we found that all such modulations can be described using essentially the same equations for bandwidth and spectral efficiency. We also talked about pulse shaping, which can be used to improve spectral efficiency, and the fact that bandwidth is inevitably proportional to data rate. Finally, we talked about the bandwidth of FM signals, which can be estimated using Carson's rule. And we identified the distinction between wideband FM and narrowband FM. That concludes this talk on signals in the frequency domain. Thanks for listening.